right, good afternoon. On admin and logistics things, what I have are two things. First is you are welcome to download the files that are now up there that I'm going to work through as examples. I'm kind of agnostic as to whether it's best for you guys to follow along with me or whether you want to just watch. I would probably just watch and try to focus on concepts. I'm not going to require anyone to be hands on the keyboard, but if you learn better by typing along with me, you can download some of those files now. Homework number 3 finally got posted. I am behind in recognition of that. I've shifted the due date back by 1 day to be Monday the 10th instead of Sunday the 9th. And also what is posted has not yet been proofread by the TAs, so there may be another version posted in 24 hours that cleans up and clarifies some wording. On the test, I will be able to finish the last piece of grading and release at about 6 p.m. tonight. Everybody has taken it, so I've posted to the Canvas the exam and the exam solution. I think that most questions, you can just read the solution key and there's not much value in going over it in class, but I will just do 2 quick things. On this very first one, the solution key just gives the answer. So that's why I'll say a few words about it. The first 2, predicting how many students will apply. Time series are relevant for both, but you had to match 1-to-1. And it's only time series when there aren't any changes in these other factors. But in question number 1, where there are changes in tuition and marketing, that's where regression has the advantage over time series because it's able to bring in those extra predictors. You can run the trend function to do linear regression with columns that are t squared, t cubed, and also columns for price and marketing. Time series can't handle those other predictors. Arguably, the second is better done with time series because regression has that problem of inability to forget the past. And the world is evolving fast enough that time series ability to pay more attention to recent evidence could give it an advantage over regression in the second. But at any rate, you got to do 1 and 1. So they're clearly the ones to go with. The third is predicting which applicants admitted will enroll. So for every applicant, you're predicting yes, no, will they enroll? That's a classic categorical forecasting method. And then predicting how large a new program will be in 5 years. You can't do that with a time series because there is no time series. You have to go far enough out into the future that you're going to want to get human judgment about the world to bear. So that's the logic for those. And the other one that I will flag, because this will cause a lot of groans. The question was, what are the numbers there? And the answer is they're all zeros. And this is one of those times when I ask for a specific number in order to test a concept. The concept is once you've added independent variables to your regression for the season, there's no more systematic being too high or too low for any of the seasons. So you can know they're all 0 without doing any arithmetic. Where I know some people are going to be very grumpy with me is a lot of you did do the calculations despite the hint, and you don't get the right answer because of just round off error. So a lot of people did all that extra work and then said, oh, it's minus 0.2 or plus 0.2 or something. But I decided to be strict on this one, even though I know you'll hate me, because I was looking to see whether you understood the concept that once you include in the regression the dummy variables for season, there's no more systematic tendency to be too high or too low. You're going to ask a question?
What happens if I just put in the formula? That still counts as full credit?
No, because I did very much ask for the values, and that's, you get the values by knowing the concept, and I was trying to test for the concept. I'm happy to take any other questions on the exam, but most of them, I think you can just look at the solution key to. And now, do you have any admin or logistics things? I did my admin and logistics announcements. Oh, I guess the last thing I should say about the exam is the mean was 65. Don't sweat it. Everything is curved. I had a computer science faculty member who really said the best exam is one where the scores go from 1 to 99 uniformly distributed, because that gives you the maximum information for assigning grades based on actual mastery of material. I don't actually aim for 50 as an average, but you guys sort of blew the curve a little bit in mini 3. This is a more typical average for my exam. So don't think absolute numbers. That's not important. Any substantive questions? Okay, so there are only 2 ideas really that you're responsible for today, and they are risk return frontiers and cumulative risk profiles, although the Nature Conservancy case is our first look at an overbooking problem, and we'll do more of those on Thursday. So I'll try to reinforce those by doing a bunch of examples, but I'm also gonna sort of page through the slides that you saw in the asynchronous lecture to give you a chance to say, wait, I actually do want to ask a question about any of them. So this was just sort of background. How does this field relate to other decision-making fields? That's fine. It's not really like you're not going to be tested on that. This is sort of common sense. Human beings make decisions all the time. It's only certain types of decisions that we follow up on, like multiple attributes on probability and so on. Payoff matrices are one of the core ideas you are responsible for this week. They're pretty simple to understand when you're looking at an example. Right? You pick a row, then the column gets determined. And the language for that is usually state of nature. It's the outcome of the dice roll. And what you get as your payoff is the intersection of the row and the column. So you're choosing a row, but you don't know which column you're going to end up in. So the right way to think about what you get when you choose a row is you get a random variable, because you get a distribution of possible outcomes that have the probabilities associated with the column. And classic advanced undergraduate, early master's degree kinds of courses will all have the concept of a payoff matrix in them and associated decision rules. What I don't like about the typical textbook treatment is it almost leads you to believe that your boss is going to hand you one of these matrices filled in with numbers and say, what row should we pick? That's not how it's going to work in the real world. In the real world, the boss is going to say, we've got to make this decision. And then you will build the model understanding the different outcomes, estimating all of the parameters, meaning the probabilities associated with the column and also the payoffs. And sometimes you might spend a person month of work just to figure out that the 3 is a 3. In that sense, the payoff matrix is really more of a summary tool that is how you capture on one page the strategic choice that's faced. And in olden times, the guidance for how to get through one of those matrices was pretty stupid because it wasn't crediting people in MBA programs or masters in public policy or healthcare policy or arts policy or entertainment industry policy or whatever, master's degrees with knowing enough probability to be able to speak with the language of random variables and distributions. But absolutely, you don't want to follow those bad rules. This is the first rule that is an actual rule you can follow, which is max EV. that is treating every one of these rows as a random variable, which random variable has the largest mean or expected value, which you find just with the sum product. And that is a totally valid and correct rule, but only if the decision maker is risk neutral. And what we need to do today is start to talk about, well, what if the decision maker is not risk neutral? And to refine that language a little bit, it's not that there are people who are risk neutral and people who are not. It's more like everybody will be risk averse if the stakes of the decision are high enough. We can all be risk neutral over very small payoffs, but we want to bring our analytic tools to bear on the important decisions, and the important decisions, or maybe to say it this way, we want to bring these tools to bear on the hard decisions, i.e. the ones for which we don't trust human beings to just know what's the right thing to do. And what makes decisions hard? One of the things that makes decisions hard is exactly that the stakes are high. So if we stopped with just max EV, it'd be like, we've prepared you for all of the decisions that you don't actually need to be prepared for, because you could probably use less formal methods. So everybody gets risk averse if the stakes are high enough, and what do we do about it? And there's, broadly speaking, these two approaches. One is what we do in this course are tools that are objective in the sense that every single analyst would produce the exact same graphs. They're not customized or personalized to a specific decision maker's risk preferences. Then in the fall course, I teach a different set of methods, which have a very different flavor. In those methods, you build your spreadsheet model of all the objective reality. What are the payoffs? What are the probabilities? And then you go to the decision maker and you interview the decision maker and ask a whole bunch of questions that are designed to allow you to literally put in your spreadsheet a model of the decision maker's risk preferences and attitudes. And once you have that model of the decision maker's preferences, then you can act as her or his agent in making choices. You can compute what it is that would make you happiest. That's a very different approach because it's contingent on there being a single decision maker who owns the decision, and that one individual's preferences are privileged in what we build in. Ultimately, it's nice to know both set of tools. Why do we do one set of tools in this class? Mostly just time. That other approach takes minimum 2 weeks, and it's better even if you have more than 2 weeks. So we just don't have time in this class to do it. But I can also make the case that in public policy analysis, it is often the public that owns the decision, not one individual. Or even if you think that you're advising Congress or a congressional committee, it's still a group-owned decision. And so there's not a single person that you can interview and have their customized individual preferences drive the decision. But there are lots of times when you're trying to advise a specific person. And so the other set of tools are useful, and hopefully I'll see a number of you in the fall. All right, so the two tools that we have are these risk return frontiers and commit versus profiles. The first one is stupid simple, and that's great because so many of the things we do in this class are so hard. A risk return frontier is literally no more than a scatter plot. So the idea is every alternative gets a dot, and the axes, and I'll just jump right to the picture, the axes have one for expected value because expected value still matters, and another axis is a measure of risk. And then you can literally see how the different alternatives perform simultaneously in terms of both expected value and risk or variability. So this particular one, I have expected value on the vertical axis, and I have a measure of risk on the horizontal axis, which you all know about, standard deviation, just a square root of the variance. And so is it big numbers or small numbers on standard deviation that indicate lots of risk? Big numbers are lots of risk. And we prefer less risk to lots of risk. So we'd like to be on the left-hand side of this. Now with expected value, do you want big numbers or small numbers? And the answer is it depends, because the answers to my questions are almost always it depends. It just depends on what we're talking about. Is the outcome profit or cost? Is the outcome species saved or tons of carbon emitted to the atmosphere? So before you figure out whether you want big or small unexpected value, you just have to think about what is it that we are looking for. So on this one, the implicit idea is expected value, big numbers are good. So it would be something like profit. And so your best of all possible situations would be in the upper left. High expected value, low risk. And then you've got a bunch of dots, which are sort of scoping out a frontier. We can still bring in that kind of thinking from chapter 7. And so you can say upper left is desirable but infeasible. Down this direction is suboptimal. We want to be somewhere on the frontier. And there's not objectively a right answer to which of the dots that's closer to the smiley face is the best. Okay, everybody with me so far? Now, how is this a little bit different than chapter 7? In the first place, we usually can't take convex combinations of alternatives. That is, the rows are just the rows. And so these are dots. You don't fill in the line in between in general. Second difference is the measure of risk should not be thought of as a sufficient statistic for everything the decision maker cares about. Or to put it differently, there's a whole bunch of different measures of risk, and none of them is right or correct. Furthermore, which dot is on the frontier can very much depend on which measure of risk you use. So real quick, this is sort of the most basic toolkit of measures of risk. Standard deviation, you know what it is, just square root of the variance. The only thing you're really going to learn here is I'll show you in a minute how you compute it from a payoff matrix in Excel. So sort of an Excel trick thing. I'm going to use that most often in my examples just because it's familiar. And I want to make sure you understand the idea of the risk return frontier. It is probably not the best measure to use professionally, though. At a minimum, you probably want to move down to the coefficient of variation because that normalizes the standard deviation for the stakes or the scale of what you're doing. If one of the options has payoffs that are $1 million or $3 million or $2 million, and the other one has payoffs that are like $3 and $8 and $0, the first one's going to have a way bigger standard deviation just because all the numbers are bigger. So the coefficient of variation divides the standard deviation by the mean, and it becomes a measure of the relative variation relative to whatever the average is. So you're probably more likely to use that professionally. Folks on the other side of Forbes Avenue in the business school believe that bigger is always better, and they don't like the idea that we should choose small. So they made the major innovation of just turning that upside down. That is that exact same ratio, standard deviation and mean, if you flip it upside down, gets called the return to risk, and then big numbers are good. And I poke fun at that a little bit, but I have briefed decision makers who could handle big is good, but not small is good. Have I told you my classic story about cost effectiveness ratios with crime and taxpayer dollars? All right, quick aside. This is just to give you a sense of what it's like as a practicing policy analyst. Very early in my career while working at RAND, I was doing crime control work. And what I wanted to do was assess different programs in terms of their cost effectiveness, meaning taxpayer dollars spent per serious or violent crime averted. Okay, so it's just going to be a simple bar, chart with columns for the 10 different programs that we were going to evaluate. And we had several person years worth of analysis to produce the chart. We were very proud of it. And RAND is very careful about its briefing. So literally the president of RAND came and was watching one of the dry runs. And he said, no, no good. Can't brief that. And I'm like, what? What's wrong? Was all this background analysis right? Ah, your numbers are all right. Just can't use that slide. I'm like, what's wrong? He said, I know the secretary you're briefing. He will not understand small bars being good. Turn it upside down and make it serious and violent crimes averted per $1 million. And as like a 27-year-old smart aleck, I was like, okay, yes, sir. We'll do it because you ordered me to, but this is the stupidest thing I've ever heard of. And the next week I gave the briefing and I came out and realized, no, President Rand was totally correct. That person could not have understood the bar chart with small bars being the best. So anyhow, you can just turn it upside down. And then to be a little more sophisticated in finance, when the outcomes have to do with how well does an investment perform, we often don't use the expected return on the alternative. We do think about things on the margin, which is appropriate. So it's what's the increase in expected return relative to the alternative of just putting the money in treasury bills. And then the right way to think about that is it's the increase in expected return relative to the safe alternative divided by the increase in risk, but the risk with treasury bills is 0. So the denominator just shows up as sigma. There are many others. I don't actually know why interquartile range is not bold. I think interquartile range is actually a really good one. And it is literally just the 75th percentile minus the 25th percentile. Or if you want to capture a broader range, you can do like the 90th percentile minus the 10th. There's nothing magic about 75th and 25th. But I like those because they're not heavily influenced by outliers. And they do capture very directly a sense of range. But whatever, the point is, there's a lot of different measures of risk. When you create a risk return frontier, you're picking a measure of risk and then just looking at the scatter plot and one dot for every alternative, figure out what corner of the graph is the best, put a smiley face there, and then figure out what alternatives are not efficient, what alternatives are dominated. And then you don't literally just cross them out though, because of this issue that something that is dominated with one measure of risk may actually look good on another measure of risk. And so here's an illustration of that idea. Now expected values on the horizontal axis will still say big numbers are good. And I actually shouldn't really have this. Oh no, the smiley face does belong up there. For both return to risk and Sharpe ratio, big is good because these are both the flipped over ones. How many dots are efficient by the return to risk measure that produces the red squares? I mean, it's 9 or 10, right? So like this is efficient, this is efficient, this is efficient. All these are on the frontier. I can't quite tell with that one. I think it may be dominated by this one because it's clear.
Yeah, we can see it.
Oh, sorry. Now you can, right? Yeah. So these two are clearly on the frontier. These three are on the frontier. This one is, those three are. I think that one's not. It's obviously to the left. I think it's below. Clearly none of these are. But I think it's either 9 or 10 that are on the frontier when we use return to risk. But with the Sharpe ratio, how many are on the frontier? Only 1, 2, 3, 4. And these are the exact same data. They're all made up data, but the exact same data will give you different ideas about how many and which dots are on the frontier. So where we're a little different than we were in chapter 7 is when something is dominated, you don't necessarily truly forget it, because maybe with a different measure of risk, it would be on the frontier.
The intuition of deciding the point
Is it similar to the ROC?
Yeah. It's similar to ROC. It's similar to Chapter 7. The two axes are both indicating something that you either like or dislike. So there's a corner of the graph that's where you want to be. So if you've got the choice, choose dots that get you in that direction. Where you want to be on this curve is a value judgment. How much do you value, how do you trade off expected value and risk? But you don't want to be below the curve. Right. So that's risk return frontiers. There's really nothing more to it than that. And so I think what we do next is go into the examples. The first thing I'm going to do is a purely abstract example with no cover story. So here's just a payoff matrix. You can look at this for a minute, and my guess is you're not going to immediately say, oh, I can just instantly say option 6 is the best or whatever. And this is not a particularly large matrix. Most years I give a homework assignment where there's like 40 rows and at least 15 columns, if not 20, 30 columns. And you apply the rules to it because you just have information overload with the big matrix. But I'm going to do this one smaller just so we can all see it. We want to find the expected value. First of all, that's what we would do if we were advising a risk neutral decision maker. Even when the decision maker is not risk neutral, they still care about expected value. It's just a sum product, i.e. a probability weighted average. That's all you do. Now, we want to find the standard deviation or the coefficient of variation, which starts with the variance. And you know from your stats class that the variance is the second central moment. Right. That's the formula for the variance of a random variable. And this captures that skater spinning around. This is the rotational inertia idea. How much is X spread out around an axis that goes through the center of mass? This is a pain in the neck to compute in a spreadsheet. So we use instead what's called the computational formula for the variance. And I'm just switching back and forth, mu of X, E of X, same thing. Hopefully in the fall, it was proved to you that these two things are the same. That's just like a algebra or calculus exercise, depending whether it's a discrete or a continuous distribution. This is easy to compute in Excel because we can find E of X squared with our sum product formula. And you just give it the probabilities and the X vector and the X vector again. To compute the expected value, we do sum product of the probabilities and the X once, that's E of X. If we do sum product of the probabilities and X again, that gives us E of X squared. So that's the convenient way of doing things. Let me, I'm going to break it up into two steps. I'm going to first do the E of X squared to make sure it's clear what I mean by that. Sum product of probabilities and X, I press a comma and I just highlight the X's a second time, put dollar signs on the probabilities and copy down. And those are big numbers, so it's not displaying. So that's just E of X squared. The variance is that minus E of X squared. This is take the expectation of the X squareds. So probability weighted sum of the X squareds. This is the expected value of X squared. And then the standard deviation is just the square root of the variance. And I guess that's what this was set up to display. And the coefficient of variation is just divide the standard deviation by the mean. So computationally, if you were asked to do the risk return frontier from a payoff matrix, those are the mechanical steps you do in Excel. Any questions about that? And if not, we'll switch over to a managerial case with a cover story.
I'm sorry.
The best because it involves donuts.
You have a favorite kind?
I do, but I've already done one digression, so professors do too many digressions. After class, I can tell you the story. All right, so I guess actually in this spreadsheet, I see how many speakers should you invite to an event. The concept here is you're going to put out a number of invitations and the invited people will not necessarily show up. And this happens all the time. For instance, we invite people to enroll in Heinz College Master's Program, and then some people accept or not. I forgot that I still had that top line. I usually teach this saying this is a party, and I'm going to have a party, and I want to know how many people to invite. And these are the payoffs as a function of the number of people who do show up. So if I invite some number of people, but all of those coins land tails and the person doesn't come, then I'm sad. If one person comes, that's way, way better than being all alone, but it's still really hard to call it a party. 2 or 3 people is fantastic because I'm like super introverted and big parties kind of scare me. Plus, I maybe didn't buy enough donuts for the party so that if there were 4 people there, not everybody would get enough. And if there were 5 or 6 people there, they would start fighting over the donuts and it'd be bloody and it'd be really, really bad. Okay, so these are my payoffs as a function of how many people come, but I have to compute the probabilities. Obviously, if I don't invite anyone, 100% chance nobody's going to come. If I invite one person, the chance that I'll get a person to come is just the probability of a head, and the chance that that person doesn't come is just 1 minus the probability of a head, probability of a tail. If we want to go past this, we want to use the binomial random variable because that's what we're describing here is a certain number of coin tosses, how many heads. So we do binom dist, and I'm interested in the number of people showing up being what's in C8. The number of coins that I'm tossing is the number I invite, which is in B13. The probability of a particular coin landing heads, that thing up in A4, and I want the actual probability, not the cumulative probability. I'll put $ on row 8, column B, and exactly A4, and then I have the probability. No, I apparently did something wrong with my $signs. Did I do wrong with my $signs? Yeah. Did I invert the order of the arguments, maybe?
Should be C. You're pointing it to the payoffs, not the number who show up.
Ah, thank you. Glad you caught that. Yeah, that's why I kind of went crazy when I got up to 50. There we go. So yeah, if I invite 2 people, what's the chance 2 show up? I have to toss 2 heads. 0.4 squared is 0.16. And this lets me fill in all of the rest of the probabilities. Now you can see that if I ask Excel, what's the probability that 4, 5, or 6 people show up when you only invite 3, it swears at me. So I'm gonna drop those out. But now I'm able to do my risk return frontier and find out how many people to invite. So sum product, the payoffs and the probabilities. The only thing that's different is in this display, I've got probabilities in the table and payoffs at the margins, but it's still the same logic. And if I were risk neutral, then I would want to invite 5 people. But what would I do if I were risk averse? Well, we can do the sum product of the probabilities
with the x's and with the x's a second time to compute the e of x squared. I did that one wrong too. Yep, I put the dollar signs in totally the wrong place. And put the dollar signs to lock in the yellow row. So C11 to I11. I think that's finally right. Standard deviation is the square root of e of x squared minus e of x squared. And there is a risk return frontier. This dot is so the standard deviation of the vertical axis, expected value on the horizontal axis. Where's the smiley face? Yep, lower right. I want a high expected value with low risk. This is what happens if I invite no one. I get no happiness, but there's no risk. If I invite one person, two people, three people, 4, 5, and 6. So what options are on the efficient frontier with this measure of risk? 0, 1, 2, not 3, 4 or 5, not 6. Was that obvious ahead of time? Probably not. Probably you would have said, I'm not exactly sure how many to invite. It depends a little bit on how I think about risk, but it'll be some continuous range. But it's not, at least with this measure of risk.
Why is 3 not on the frontier?
Because this dot is both to the left and higher than this dot. So the dot that I'm now pointing to dominates the dot to its left. And I can just move along. This is 0, 1, 2, 3, 4, 5, and 6. And you could read that off if you wanted to by looking at this and this. In fact, let me just do this. So you can see if I select the data I'm just using are, it's just a scatter plot. Okay. So the punchline here is, okay, we saw some mechanical steps, and it gives you a hint that sometimes the risk return frontier will have some information that you wouldn't get otherwise. This sheet is literally the exact same thing. All I did was, this is the exact same thing. All I did was invert it. So now the number invited is determined by a column. The number coming is by row. I literally just transposed it. And I did that because in many cases, when we use Monte Carlo simulation in Excel to inform a decision, it'll be convenient to have the different options available to us in different columns. So we're going to choose a column. And since most of my problems are twisted over like that, this is that. And I'll do the steps with a bigger party inverted like that, because you guys are not as introverted as I am. You probably would want to consider bigger parts. So here I have payoffs for anywhere from 0 to 100 people coming. The ideal number of people to come is 70. And the number of people we're going to invite can basically be 30 to 100. So this is a party that's kind of the size of a policy master's program. This is essentially the same formula we just used on the previous slide. It's the binom dist. The only thing that's changed is I put it inside an if statement. And the if statement says, if you're asking what the probability is that more people will come than you invite, don't swear at me, just leave it blank. So it's a way of suppressing those # num errors, because I want to be able to run the sum product. Everybody okay with that? It would take me a long time to go back and delete all of the swearing. So this is just going to save us time. Oops, one more column. Now let me ask, is it obvious how many people to admit? I think the answer is no. This is like just a little bit too big. You're not going to just intuit it, but we can do the steps easily enough. The expected value is just the sum product of probabilities and the payoffs. I'm going to copy this left to right. So I'm going to want to put $signs in front of the B's. So I lock in referring to that payoff column in column B. And when I copy it left to right, the columns of probability will change. Standard deviation, going to use this formula. So it's the square root of E of X squared. That's the sum product of the probabilities with the X's with the X's again. And then I will subtract off the expected value squared. The expected value is in cell C6. And I'm going to put $signs for both references to column B. So I can copy this left to right. And because this is a more professional application, I also want to not just use standard deviation, I'll do the coefficient of variation as well. And there's my risk return frontier. All right. It's just computing the expected value and standard deviation for each of those different alternatives. Where is the smiley face? Again, it's lower right. We want high value with low risk. Low risk for standard deviations is low numbers. What's on the frontier? Well, this is on the frontier. This is on the frontier. That is not. There's actually two dots down there that are, and that one probably isn't. I think that has moved to the left. But if you're not sure, you would just go back and look at the numbers instead of trying to read off the graph. This is no good. These dots, if you look at this, is like 563.786. That's admitting 94 students, 92 students, 90, 88, and that's 86. But admitting more than 86 or 87, yeah, definitely don't want to do that according to this measure of risk. If you're down here admitting 30 students, well, it's not literally dominated, but the way you read the graph is we can get a whole bunch more expected value for a pretty small increase in risk. So realistically, you're probably interested in these dots here. 650.1 and 31.7, 654. Those are 80 and 83 students. Okay. Questions about how to read the graph or what it means? All good. By the way, the options up there on row 11, 30 to 45 to 60 to 70, and then 82, 83, 84, really? Yes, really. So the way you would do this is you first have a very coarse search with big jumps to figure out roughly what's the right area to be. And then you zoom in by moving in smaller increments. Oh, good. All right, that's risk return frontiers. One more example. That makes the cover story better yet. So I ask you to read this one. So Nature Conservancy wants to raise money. This is social entrepreneurship. They're a do-good nonprofit, but they don't want to be dependent totally on foundations. So they're going to provide a service to try to generate some revenue to cross-subsidize some other activities. And so their bright idea is we're going to run tours and we're going to charge a Cadillac price, $100 a person. Up to 20 people per boat. So a full boat would generate $2,000 in revenue and only cost $1,500 to run. So every full boat generates $500 in positive net revenue. The catch is not everybody shows up. There's no shows, just like in many things, like admitted students don't enroll, airlines sell a ticket and the person doesn't show up. And also because we're charging such premium service, we're going to give the money back to the person who doesn't show up. So it's a refundable ticket, refundable up until the last minute. And the other catch is we guarantee we'll never say boat's full, you can't go. So anybody who shows up, they're going to need to go on a boat, which exposes us to this risk. You know, suppose you sell 21 tickets, 21 people show up, you're stuck running 2 boats, and that'll cost you $3,000. You'd only have $2,100 in revenue, you'd actually lose money. All right, so how many people do you think, how many tickets do you think we should sell? So 2 questions. One is it obvious? It's a pretty simple problem, but it's still not obvious. And here's how many people who haven't taken a class like this would think. They'd say, oh, 80% of people show up. Let me sell 25 tickets because then I'll probably get 20 people to show up, and 20 people is great because I'll just exactly fill up a boat and I'll have $500 in revenue on average. Or if I'm a little more ambitious, sell 50 tickets because then 40 show up and I just fill up 2 boats. That'd be great too. And I'm not exactly sure how it's going to turn out. I can tell there's some risk. Maybe it's not going to be quite as good as that. So I'm prepared for being a little bit lower, but surely selling 50 tickets will basically just double the result with selling 25. All that's totally wrong, right? Why is all of that totally wrong? You should know it's totally wrong because the expected value of f of x is not the same as f of expected value of x. And that reasoning is that. It's plugging in expected values to a nonlinear function. And that is, I mean, might as well just commit suicide because it's quicker and less painful. So how can we really analyze the problem? We need a probabilistic model. And what I'm going to do here is solve this once the same way we did the donut problem and the party problem. And then I'm going to solve it with Monte Carlo simulation, because the learning objectives here are I want you to understand what a risk return frontier is, but I don't even expect you necessarily to be able to do the party problem. And certainly I don't expect you to be able to do one much beyond that exactly, but you can simulate anything. And so I'm going to solve it both ways, and then we're going to contrast the risk return frontier that's exact with the risk return frontier we can get via simulation. All right, so here we go with exact. This is again oriented where we're choosing a column. We choose how many people, in fact, I even still have it listed as number invited. It's obviously, I copied over the same sheet from before. It should say number of tickets sold. And the formula here for probability is the exact same thing as before. It's essentially binomial distribution, finding the probability, but I've got an if statement there because the probability of getting more than, wait a minute, so I have to go over to and 64. There are places where if you ask, what's the probability 35 people show up if I only sell 20 tickets? The right answer is 0. I don't want an error. All right, we'll do the same game again. The expected value is just some product of the probabilities and the payoffs. Oh, I guess I should back up and explain the payoff column. It's probably pretty obvious. Profit is revenue minus cost. Revenue just is $100 per person who shows up. And the cost is $1,500 times the round up of number of people who show up divided by 20. Exact same as that tuition setting example from the very first class in E3. And the profit is the difference between those two. All right. Standard deviation is the square root of the sum product of the probabilities and the x's, and the x's yet again, e of x squared part, and then subtract off e of x squared. That gives us 1 dot, but I want to put $signs on the references to column C because I'm going to want to copy this across. Oh, I actually don't know why I have e of x squared there. I did it all in one step. All right, so in a minute, I'm going to release this. Just take a second and write on a piece of paper or think, what's the basic shape? You saw for inviting a party that it was kind of like that. Is this going to look like that? It's going to be expected value and risk. Is it going to be convex? Is it going to be concave?
These spikes when you have to do it in both.
So you're remembering our stegosaurus picture. So you think it's going to be looking like a stegosaurus?
Well, not exactly because.
Oh yeah, you're right. It's different axes, but we'll see jumps. We'll see. Yeah. Anybody else? Has everybody made your mental guess? How many of you think it's going to look like a pretzel? I mean, you saw that coming, right? That was like obvious. All of it. I know you all thought it was going to be a pretzel. You were just shy about. How good is our unguided human intuition at thinking about? Yeah, we're hopeless. All right, so the axes again, expected value, standard deviation, smiley face is on the lower right. This dot at 178.8 corresponds to inviting 20 people. So it goes like this. This is 20, 21, 22, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40, 1, 2, 3, 4, 5, 6. I think that's 40 to 44 to 46, 47, 48, 49, 50, yada, yada. All right, so what is on the frontier? If you are pedantic about it, you would say this dot, maybe that dot. In fact, maybe even all of those and definitely those three. But if you're not pedantic about it and you're being a practical manager, you'd say, look, I want to be in one of those three. Maybe down here, but really not making very much money. At that point, you might not want to do the thing at all. So probably these 3 dots. And those 3 dots, 497, 542, 560 are, yeah, 44 to 46. That's sort of the right number of tickets to sell. How would we have done if we sold 25 tickets? Let's see, 25 tickets is minus 131,594 there. That's what happens to people who sell 25 tickets. They actually lose money on average and expose the organization to risk. Are they likely to get promoted? Probably not. All right, so 25 is bad, and you realize the reason is asymmetry in the type 1, type 2 error payoff kind of thing. It's a nonlinearity, it's a kink in the payoff function. But whatever, that's now clear. But surely selling 50 tickets is going to basically be double selling 25 tickets, right? All right, so remember that dot. Where is the dot for 50 tickets? Dot for 50 tickets is 334,547. 334,547 is this. Is this dot twice as far from the origin in a particular direction than that dot? Not at all. Because they're not like independent things. It's not like you sell 25 tickets and then however many show up, you do your thing. And then that boat is sailed, and then you have the next 26 to 50 come. There's an interaction between the two of them. So there's no way that selling 50 tickets is more than selling 25. All right, hopefully at this point you say, cool, I do need help thinking about even simple problems with probability, and I got some insight out of this, but you also are probably thinking, oh, this is totally hopeless. I'm not gonna be able to do this myself. And that's fine, because I don't expect you in general to be able to do exact calculations. I want you to be able to do simulations and come up with the approximate expected value and the approximate standard deviation, and then work with that. So that's what we're going to do here. Again, 20 and across, here are my parameters. Now let's fill this in. How many people will show up in our simulation if we sell 20 tickets? So that is crit binom. The number of trials is 20. The probability of a head is 80%, and we feed it the random number generator. And now every time I press recompute, that thing wiggles. Now, what's my revenue? My revenue is just $100 times the number of people who show up. What is the number of boats I need? It's the round up of the number of people who show up divided by the size of the boat with 0 digits after the decimal point, meaning integer number of boats. Our cost is $1,500 times the number of boats. And our net revenue is revenue minus cost. And that is what we want to simulate, that net revenue. So I can copy this across. And if I press recompute, I'm getting the beginnings of a risk return frontier. As I'll explain more on Thursday, this is not the ideal way to do the simulation because we're not comparing the columns on a level playing field. This is actually a great roll of the dice for making this point. Here I'm saying if I sold 20 tickets, 18 people show up. If I sold 21 tickets, 14 would show up. Yeah, both those things are possible, but this column was an unlucky column in the sense that an unusual number of tails were tossed. And we'd rather compare all of these columns with the same result for the first 20 coin tosses. So instead of using separate calls to crit binom for all of these, a better way to do the simulation is say, all right, I got 15 heads on those first 20 tosses, and now let me toss one more coin. So if a random number is less than 80%, you get one more person showing up. And now these number of people showing up will based on the same coin tosses for every one of these columns. And that creates a level playing field. Does that risk return frontier that came out of simulation look anything like the one that we got the exact way? Well, here are the two of them plotted on the same axes. And you have to look close to even see the difference between them. And that wasn't just dumb luck from that particular set of 10,000 trials. I'm now clicking, and if you can see the blue moving just a smidge, that's the amount of variation we're getting from trial to trial. And if that amount of variation bothered you, which I really don't think it does, then you just run more trials. So the meta lesson there is, even if you can't do exact calculations of probability, putting Monte Carlo simulation together with risk return frontiers gives you a powerful tool for guiding decision. Next, got to get to that next tool. Oh, I forgot that I'd even given you that pretzel. Glad people didn't look ahead. Okay, yeah, that's the picture that shows red and blue sitting on top of each other. Second tool from today is called cumulative risk profile. This is literally, the distribution function for a random variable and the outcome of something has a distribution of possible values. This is just the cumulative distribution of that random variable. So the notation that we use is usually capital F, the name of the random variable, and then an argument, and it's equal to the probability that that random variable is less than or equal to that particular outcome. And cumulative distribution functions are always monotonically non-decreasing. They start off at 0 for minus infinity. Because if I ask, what's the probability your random variable is less than minus infinity? It can't be, so 0 probability. If you go all the way over to the right, you're asking what's the probability your random variable is less than or equal to positive infinity? Always less than or equal to positive infinity, so it always comes up to 100%. And as you increase the argument, you increase the probability that the random variable falls below that cutoff. So the cumulative distribution functions will always look roughly like this. And their power is they can sometimes help you resolve different distributions that are hard to resolve either with the risk return frontier or with the simple distributions. I'll show this example in just a moment, but for now, just do those two lines lie on top of each other? And you can tell which one is better. The only trick about this is you've got to think left and right because the horizontal axis is capturing the payoff. Don't think up and down, think left or right. So suppose the outcome here is a good thing, like profit or lives saved. So we like big numbers. The blue curve is to the right of the red curve. It goes with bigger numbers. You want the blue curve. If the outcome was cost or number of species driven extinct, then you would like low numbers, which means you want to be on the left. So you would want red. But that you have to slow down and think about because go back to profit. I want big profit. I want to be up, right? No, because the vertical axis is the probability. The horizontal axis is the payoff. So you got to think, do I want to be left or right? So let me pull up. Okay, you have to make a choice between option 1 and option 2. Option one is somebody's going to quote unquote roll the dice and take a draw from a normally distributed random variable. And that's the number of dollars that you're going to be just given. Mean of $45, standard deviation of 15. Option two, the exact same thing, except the mean is 40. All right. Which option would you like to take? Not a trick question. You'd rather have option number one. Totally obvious, right? Well, here is the simulation, right? I'm generate these random variables, they wiggle. I've done a Monte Carlo simulation, 10,000 trials, and here are the histograms, the result. Are those histograms well resolved visually? Not super. I mean, if you look at it, you can tell blue is to the right of red. So yeah, I want blue, but you kind of got to squint or look at it for a little bit. But what about the cumulative distributions? Where are they? There. If I look at the cumulative distributions, can you tell that blue is different than red? Now it's very easy to see that they are different. You just have to remember to the right is good. What is this cumulative distribution function? It is again just a scatter plot. How do you create them? Well, as a practical matter, you're going to create them by using the template that I gave you. So on the homework problems, just open up and work with this sheet. It's all set up to create it for you. But what does the sheet do? Not much. All you do is you type in these numbers, 1 to 100%, and then you ask Excel over the 10,000 simulation trials, what is the percentile that goes with that? And it kicks out the value on the horizontal axis. And then the cumulative distribution functions are literally just scatter plots of those points. I wanted to show the data. So it's just, this is just column V plotted, the column W plotted against column V. That's all the plotting points are. Once you've done the simulation, this is just collecting the percentiles and then plotting them and putting a smooth curve for them. So again, it's super easy to create. It is a little harder to interpret than the risk return frontier, but it's useful. Suppose you had to choose between options 1 and 2 in terms of risk return frontier, right? Imagine those as the plotting points on a risk return frontier. Does one dominate the other? You want a big average, you want a small standard deviation. Does either option 1 or option 2 dominate the other? They don't. So you do it sigma, mu, they look like that. Neither is unambiguously closer to the smiley face. So if that's the only tool you've got, you would have to tell the decision maker, don't know what, boss, can't help you. But now look at the cumulative risk profiles. Looking at the cumulative risk profiles, can you tell that blue is better than red? There's a formal way of talking about whether or not blue is to the right of red. And I'll just mention the words, but this year I'm not going to test you on them. It's called stochastic dominance. So there's first order stochastic dominance, second order stochastic dominance. I have found over the years teaching those tends to confuse people, so I'm not going to burden you with it. But if you hear the words, those are words that essentially are related to, is one of these curves to the right of the other curve, including being able to think about instances where it's not clear cut. So that's first order stochastic dominance, that's second order stochastic dominance. I'm not going to quiz you on second order stochastic dominance, but I do want you to know you can create these cumulative risk profiles, and they can help resolve situations that the risk return frontier alone will not. Okay. We have time for one more example. I think I'm going to do this one. This is a very practical example, and it pertains to an important concept called real options. It's described in detail in that chapter P that I had you read part of last week. So if we don't quite finish it, or if you want more time to digest, this is all written out in chapter P. So here's a story. We do not know how much demand our organization is going to face, but we have to build a factory to get ready for it. It doesn't matter whether it's a factory, we have to build capability. And we basically have two choices. We can build small or we can build big. If we build small and demand is big, we miss the opportunity to do well. If we build big and demand is small, then we lose money. And it'd be the same principle if it's uncertain how much healthcare demand there's going to be in a region, and you can build a small hospital or a big hospital. But I've framed this as a factory. In particular, we have two sources of demand. One is our traditional market, but even with the traditional market, there's a lot of uncertainty. It could be anywhere between 40 and 140, but there's an 80% chance we'll get a new market. And if we get the new market, that will produce an additional 30 to 80. So at worst, we could be down at 40. At best, we could be up at 220. There's really a lot of uncertainty about demand. Our basic option is we can build small. That gives us the capacity to produce 90. And the marginal benefit per customer served is 1,000. It costs us $85,000 to build small. And so if we build small, there's no way we can do better than 5. We could get 90 in revenue, we'd have 85 in cost. We're capped. No way you can do better than 5. And if demand is below 85, you're going to lose money. The other option is you build big. If you build big, the capacity is twice as big. Capacity is 180. And building big doesn't cost twice as much because there's economies of scale in construction of the factory. So we could build capacity to 180, but now the cost is 130. So if demand is below 130, we're going to lose money. And we have very little chance of beating 130 if we don't get that new market to open up. So Mo, if you know the Three Stooges, says go with a small plant. Larry says, heck no, go big or go home. And Curly says, I think there's too much uncertainty here. Let's slow down and buy a real option. An option just means you spend money now to acquire flexibility in the future. And the nature of this real option is you buy a big parcel of land and you start with a small factory, but you design it so that you could later expand it. The option costs money. It costs $10,000. But it allows you to then build out the bigger plant, not for an additional 90, but just for the same cost that it would have to begin with. So if you end up buying the option and then building the plant that's big, your total cost is 140. The 130 for the big plant plus 10,000 for the option. The other two say Curly is crazy. Mo says Curly is crazy because no matter what happens, you're going to spend $10,000 you didn't need to spend. And Larry says this is totally crazy because you would be spending $95,000 to build the small plant, which has a capacity of 90 if you don't exercise the option. So you are guaranteeing that you would lose money if you pursue the option. And demand is not that high. So why not just build big? So the CFO has listened to all Three Stooges and is confused, and you're supposed to use simulation to sort this out. Everybody understand the problem?
Should have included that they all poked at each other.
Oh, absolutely. They poked each other in the eye. That's why they couldn't see the answer. I'm sorry, you asked for that. I wouldn't have done that if you hadn't set it up. I'm just gonna show the solution, not build it. So random number is demand from the traditional market. Just random 0 to random 40 to 140. This is the demand that we would get from the new market if the new market comes along. This is that Bernoulli or binary random variable, yes, no, does new market emerge? And then this is total demand. We're guaranteed the demand in cell D3, and we might get the demand in D4 only if the new market appears. Sales is the minimum of capacity and demand. So nonlinear min function, warning, the reasoning on averages won't work well here. And it's min regardless of whether we go small or big. The only thing that's a little tricky is with the option, the sales are basically the same in either, but now we have a choice. We can either stay small, in which case it costs us 95,000, or we can make the plant big after we know how much demand there is. These two numbers are both just 10,000 worse than those numbers because we have to pay for the option. But with the option, we then get to choose. After we've seen what demand is, we get to choose whether we want to keep the plant small or expand it. All right, so it's just a simulation. We peel off Mo's, Larry's, and Curly's profits, and then just for fun, that's the distribution of demand. And I've run the simulation, how many times it is. This is 10,000, and there's our table of results. If the CFO is risk neutral, whose plan is best? Curly. Curly has the highest expected value. If the CFO is risk neutral, expected value is a sufficient statistic. It's all you need to know in order to figure out what to do. Now, think risk return frontier. Using standard deviation as our measure of risk. What would you tell the CFO? If that were a good measure of risk from the CFO's perspective, are any of the three plans dominated? What about Larry's plan? Compare Larry's plan to Curly's plan. Which is better on expected value, Larry or Curly? Which is better on standard deviation, Larry or Curly? So if you're doing a risk return frontier type analysis, you drop Larry's plan, but Mo and Curly both survive because Mo offers lower risk and lower expected value. Curly offers higher risk, higher expected value. So if you only know risk return frontiers, you can do a little bit, but you're stuck there. And also, you had to assume that the standard deviation was a good measure of risk for the CFO, and that's a little bit uncertain. So how about we look at the cumulative risk profiles? Oh, they're down here. All right. Do you want a curve that's high, low, left, or right? Right. So when you're reading cumulative risk profiles, you think left, right, not up or down. And this is net profit or profit. So big numbers are good. What curve is, what do you see now in terms of which curves are rightmost? there's no simple dominance going on here. It's not like that previous example where guaranteed for sure. But Larry's plan is way spread out. The fact that the cumulative risk profile, which will always go from 0 to 1, takes a long time to get from 0 to 1, is telling you lots of different things can happen with Larry's plan. So Larry really does have quite a bit of risk. By contrast, Mo's plan does not have very much risk. Mo is the go small. That's the lowest risk, and you can kind of see that it's pushed together. But if you compare red and blue, if you compare Curly and Mo, with Curly's plan, you're giving up a little bit here, but you're winning in kind of a big way there. That does not mean the CFO should go with Curly. That is still, depends how risk averse the CFO is, but this is a way of just seeing in a picture that trade-off between expected value and risk. And that's all we can do in this class with these tools. Risk return frontiers and cumulative risk profiles are just ways of turning into a picture the trade-off between expected value and risk, helping the decision maker see and make a judgment. In the fall class, we go that step farther and say, let me ask you a whole bunch of questions and try to literally build into the analysis your preference. Right? Thursday is mostly just more practice of this sort of stuff. See you then.